Today we are going to start chapter 17. Yes, I have uploaded updated files of section 4.7 and 4.8 where I solve some more questions similar to what we did before, just for your practice. You solve more questions from the book, make everything clear. If anything not clear, let me know. We can discuss it here. Chapter 17, 17.1. In chapter 17, we will be doing many sections like 17, 1, 2, 3, 4, 5, 6, 7, 7 section from this chapter. And then similar, any complex integration in chapter 18, 18.1, 18.2, 18.4. And then we will come back to Taylor series and Lawrence series. Okay, first of all, you know that in complex numbers, we have a real part and imaginary part is the one with the complex number I. So I we are using here will be equal to square root of -1. So, and a complex number is denoted by Z and it is equal to A plus IB, where this A is called real part and this B is imaginary part. Only B is imaginary part. What is making it imaginary? This I. So what is with I? That is imaginary part of the complex number. And what is without I? That is real part of the complex number. And two complex numbers are equal if their real and imaginary parts are equal. So let me say with the dot, let me say what is equality. Z1 equal to A1 plus IB1 and we have Z2 equal to A2 plus IB2, Z1 equal to Z2 if and only if A1 and A2 are equal, B1 and B2 are equal. So, and then next we have how we add complex numbers, same Z1 and Z2. We have Z1 plus Z2 with A1 plus A2, any real part with real part and imaginary part with imaginary part. We add them by adding real part with real part and imaginary part with imaginary part. So this today's lecture is very elementary. Similarly, subtraction. In the subtraction, we will subtract real part from real part and imaginary part from imaginary part. And if we have a minus here, that will be here and here. In between, we will have plus I. And how do we multiply? multiplication of complex numbers is Z1 multiply Z2 is A1 plus IB1 A2 plus IB2. This is equal to A1 A2 plus I A1 B2 plus I A2 B1 plus I square B1 B2. Now here A1 A2 is real part and I is -1 square root, so I square will be -1. So negative B1 B2, this is real part and I take common factor A1 B2 plus A2 B1, this is complex part. So we multiply them by distributive property and we can also divide two complex numbers. So the division is if we have Z1 over Z2, we do intaqal maqam rationalization. A1 plus IB1 over A2 plus IB2. We multiply by the conjugate of denominator. So A2 minus IB2, A2 minus IB2. And what do we get here? We get A1, A2, and then negative I square B1, B2. So plus B1, B2, real part, and imaginary part is A2, B1 minus A1, B2. A2, B1 minus A2, B1 minus A1, B2 over A square and plus B square. Only A square plus B square, the other part will cancel out. And yes,
it should be A2 squared plus B2 squared, I think.
you are right. Yeah, I forgot to here.
Victor,
Yes, please.
in the addition above, you wrote Z1 plus minus Z only, not Z2.
In addition, Z1, Z2. You mean this one?
Yes.
Yeah. Okay. Division and it satisfy the commutative law, associative law, and distributive law. Complex numbers like real numbers, they satisfy. Commutative law. Commutative law mean Z1 plus Z2 is same as Z2 plus Z1. And associative law or property is that if we have Z1, add in Z2 and Z3, this is the same as we add Z1 and Z2 first and then we add Z3. Also, it satisfies distributive law. That one complex number can be distributed over two or more complex numbers Z1, Z2, Z1, no, it should be Z3 here. So Z1, Z3. These are very basic elementary properties of complex numbers. You must have seen them somewhere before. And what I have used before is called complex conjugate or simply conjugate. Complex conjugate of a complex number is denoted by Z bar, and that is equal to X minus IY. And the properties this complex conjugate satisfy is that conjugate of sum of two numbers is sum of their conjugates. Conjugate of product of two numbers is equal to product of their conjugates. And similarly, if we have Z1 over Z2, any conjugate of division is equal to division of their conjugates. Again, these are simple basic properties of complex numbers. How we add, subtract, multiply, and then absolute value or modulus. If we have Z equal to X plus IY, then this in geometrical representation, this complex number, suppose we have here, this is complex number Z. Now x-axis is called real axis and y-axis is called imaginary axis. And then the modulus of Z is actually this distance. Modulus of Z denoted by this absolute sign. We call it modulus or absolute value. And that is equal to real part square plus imaginary part square. Now we note that if we multiply a number with its complex conjugate, yani x plus iy, we multiply with x minus iy, this will be equal to x square minus ixy plus ixy will cancel out, minus I square y square, and I square is minus 1, so we'll make it plus 1 and y square, and this is equal to z absolute square. So z absolute square is z times its conjugate, complex conjugate. And next is the exercise. Very easy, very simple, very basic. Also, uh, powers of I. You know, I is -1 square root. Then I square is -1. I power 3 will be -I. And I power 4 is +1. And this cycle will repeat itself after 4. So if we have a number bigger than 4, we divide it by 4 and take the remainder. For example, if power is 6, I power 6, this is equal to I power 2, because when we divide 6 by 4, then the remainder is 2, so that is equal to the remainder. So is equal to the remainder. Remainder after dividing this number by 4. So we can say that for a if, let us say it like this one, if so n is bigger than 4, then I power n is same as I power, let us call it as a I power r, where r is the remainder r is the remainder when after dividing or when we divide n by 4. So when we divide n by 4, what is the remainder? That is r. If you have any question, you can ask me anytime. Exercise 17.1. The first 26 questions are to write the complex number in form of a plus bi. So let us first practice about this I. We have I power 3, I power 5 minus I power 4 plus 7 I power 3 minus 10 I power 2 plus minus 9. Now 3 I power 5, when we divide 5 by 4, the remainder is 1, so 3i. I power 4 is 1. I power 3 is a negative I. I power 2 is a -1. So this is equal to 10 minus 9 is 1. 1 minus 1 is 0. So 0 minus 4i. This is in form of a plus bi, where a is 0 and b is -4. In a is 0, b is equal to -4. Then we have sum, difference, multiplication, division, so on. For example, question number 12, 1 minus I power 3. So by the binomial expansion, we have 1 power 3 plus, or since it is minus, so let's write directly minus 3 multiply 1 multiply 1 square multiply I plus 3 multiply 1 multiply I square minus I power 3. Similar to a minus b cube. A minus b cube is equal to a cube minus 3 a square b plus 3 a b square minus b cube. So this is 1. 1 square is 1, so minus 3 I square is minus 1, so minus 3 from here. I cube is a negative I, so plus I. So this become negative 2 minus 2I. So this is a plus b form where a is negative 2 and b is also negative 2. And division of complex number, I just told you before. Let us see what is question number 19. Question number 19. It is 5 minus 4i, 3 plus 7i. Over 4 plus 2i plus 2 minus 3i. We need to write it into a plus bi form. So first we will do this addition. 5 minus 3, 2, negative 4, negative 7, negative 4, I minus 7i, 11i, divide by 4 plus 2, 6, 2i minus 3i is minus I. After this, we will multiply by conjugate of Mukam, which we call as Intakal Mukam. So 6 plus I, 6 plus I. In denominator, it is a number with multiply by conjugate. So it is 6 square, yani 36, plus 1 square, yani 1. In numerator, it is 12 minus plus 2i minus 66i minus 11 I square, so plus 11. So this is equal to real part 11 plus 12, 23 minus 64 I over 37. So we write it 23 over 37 minus 64 over 37 I. So this is in form of a plus bi. Any question? What can be easier than this at this level?
Doctor,
Yes,
we have a point in the first quartile, then the vector from the origin to this point is a complex number.
You see, in complex plane, like maybe you are seeing in book, they are denoting it by vector. So this vector, let us, if we make this as a vector, then this is a position vector. A vector which is starting from the origin, a vector from whose initial point is at the origin is called a vector in standard position. Okay. And it is not associated with quadrant. It can be in any quadrant, first, second, third, fourth, wherever it is. Now, we can make a position vector. Now, this position vector is telling us many things. Number one, it is a vector from the origin to this point. So if that point is maslan 2, 3, that vector will be 2i plus 3j. And here I'm putting hat on this one because no, I hat is not a complex number I, but it is a unit vector in the direction of x-axis. So when we have a vector in standard position, the components of these vectors are actually coordinates of the endpoint. Like if a point is 2, 3, and you make a vector with the starting point at the origin, you get 2 plus 3i. So if you look a point, you can make a position vector. If you look a vector in standard position, a vector in standard position mean its initial point, starting point is at the origin. So when we look at a vector in standard position, then its components are the coordinates of the endpoint. Okay, so these things are related to each other.
So we can write it like, for example, 2ax plus 3i ay
2a
x.
X is coming from where?
Ax is the unit vector as we studied.
Oh, so you are saying like this. So yeah, we can write 2a sub x hat plus 3a sub y hat.
But now 3 is imaginary part, so can we write j?
No,
3j?
here when we are writing this, in vector form, then 3 is imaginary part, or 3 is the y coordinate, whatever you can call it. It is imaginary part or it is the y coordinate of the end point. Okay.
Okay, so we don't need to write j.
You don't need to.
Write j if he give me a point in the complex number,
No,
and
you
he
know,
ask.
you mean j like this?
No, j or I is the same, man. Root of -1.
Yes. So here, no. In the vector notation, we will not write this one. No.
Okay, this is
But
my question. Yeah.
yeah, but this vector should be in the position vector so that the starting point is origin. So if we have a vector, it gives us the end point. And if that end point is in the complex plane, then we have the complex number from the vector. So we have a complex number, we can write a vector. We have a vector, we can write complex number. So these are some few very basic say operations on complex numbers, and similarly in 37, 27 and 32 they are asking us some other things. For example, in question number 27 they are saying that what is real part of 1 over z. It is not 1 over y. First we will see what is 1 over z, yani 1 over x plus iy. So 1 over z equal to 1 over x plus iy, and whenever we have a complex number, any I in the denominator, we do this in Takal Maqam. So this is equal to x minus iy over x square plus y square, which we can write x over x square plus y square minus I y over x square plus y square. So real part of 1 over z is x over x square plus y square. And similarly, real part of z square, yani z multiplies z. Real part of or imaginary part of something similarly we can get whatever it is. If we have maslan z plus 5 times z bar, what is its absolute value? Okay, it is x plus iy plus 5 times x minus 5 times iy, 5 iy or 5, you can say 5yi, whatever you call it. So here we have a real part as a 6x and imaginary part negative 4yi. Yes.
Doctor, is it plus 5y? Not minus.
Not minus. You look at z with 5.
Oh, Z bar, I didn't see it.
No problem. No problem at all. So 6x minus 4y. So absolute value, it is 36 x square plus 16 y square and square root. Okay, now in complex numbers, we don't have one thing, and that is positive or negative complex number, or a smaller or bigger complex number. Yes, but we can say that a complex number is close to the origin or far from the origin, and that we will determine by taking its modulus. For example, in question number 39, which of the complex numbers is closer to the origin? And what are complex numbers? 10 plus 8i and 11 minus 6, sorry, 6i. So 10 plus 8i, we will take the absolute value of this one is 100 plus 64, which is 164 square root, and 11 minus 6i, it is 121 plus 36, which is equal to 157. So the distance from the origin to 10 plus 8i, yani its absolute, is 164, and distance from origin to 11 minus 6i is 157. So we say that 11 minus 6i is closer to the origin. We can say like this one. And like we were doing in previous chapter also, question number 41 is that Z1 minus Z2. What is Z1 minus Z2? Z1 absolute, Z1 is X1 plus I Y1 minus Z2. So minus X2 minus I Y2. This is X1 minus X2 plus I and Y1 minus Y2 absolute, which is equal to X1 minus X2 square plus Y1 minus Y2 square root. So this is distance between the 2 points, which is the distance between 2 points which are represented by complex numbers Z1 and Z2. So Z1 minus Z2 is actually distance between 2 points in the complex plane. And also these complex numbers, they satisfy another thing which is called a triangular inequality. Triangular inequality is that Z1 plus Z2 absolute is less equal to Z1 absolute plus Z2 absolute. And this property is not true only for two complex numbers, but it is true for any number of complex numbers. Z1 plus Z2 plus Zn is less equal to Z1 absolute, Z2 absolute, and Zn absolute. Also, we can write we can obtain another important property is that Z1 plus Z2 absolute is greater or equal to Z1 absolute minus Z2 absolute. You can also say greater or equal to Z2 absolute minus Z1 absolute, whatever you can say, or greater or equal to Z2 absolute minus Z1 absolute. So we say that Z1 plus Z2 absolute is smaller than their sum of the absolutes and bigger than their difference of the absolutes. Bigger than the difference of absolutes and smaller than sum of the absolutes. Triangular inequality, and that's it. Now, this is section 17.1. There are several more questions, very similar to what we have done so far here. Next section is 17.2. That is powers and roots. So first section was very basic properties of complex numbers, operations on complex numbers. And now next section is a little more complicated, or we say that more interesting. Powers and roots. Powers is also easy, but roots will be something to do. I mean, roots, to find roots will involve some more calculations, computations. But before we go to look for powers and roots, let us see one thing from here. Let me make it in black color. Suppose we have a complex number, and let us say this is the complex number, and this complex number has the real part as, let us say, x, and y value, yani imaginary part, let us say y. So if we write it in the real plane, we will write x comma y. But if we write in complex plane, yani this point, we write this point in complex plane, we will write it as z equal to x plus iy. In real plane, x comma y, here x plus iy. Now here, the real part and imaginary part, they give us this triangle in which from here to here is the real part and this is imaginary part. Suppose the line from origin to this point, we call it as R, denote it by R, and the angle what this line is making with the real axis, let us call it as theta. So if we have z equal to x plus iy, and this is making angle, the line from origin to z, the line from origin to z suppose it is making angle with positive x-axis theta, then x is equal to r cosine theta, y equal to r sine theta. So then the polar representation, polar form of the complex number. So let me start with this one with the heading polar form or representation of complex numbers in polar form, that we have z equal to x plus iy, then x is r time cosine theta and y is r time sine theta, where we need to remember that r is distance of the point from the origin, yani r is equal to x square plus y square square root, which is equal to modulus of z, and theta is tan inverse of y over x, tan inverse of imaginary part divided by real part. So with this we can write z equal to r cosine theta plus I. So r is mushtarik, cosine theta plus I time sine theta. Cosine theta plus I time sine theta. So we can write it like this one. And let us see some example. If we have z equal to 1 minus square root of 3i, so which mean that z is equal to 1, sorry, x is equal to 1 and y is equal to negative square root of 3. This is in quadrant number 4. R is equal to 1 plus 3 square root, which is equal to 2, and theta equal to tan inverse of negative square root 3 over 1. Okay, now for you, maybe you don't remember what is the tan inverse of negative square root 3. So you can do this also. Since x is equal to r cosine theta, so you can say that cosine of theta is x over r. What is x? X is equal to
1.
1. R is equal to 2. And sine of theta is negative square root 3 and r is 2. Now just forget this negative sign and think what is the value of theta which give you sine as a square root 3 over 2 or cosine as 1 over 2.
60.
So that theta is
Pi
equal
over 3.
to pi over 3. So this is number 1. Ignore the sign, negative or positive. Just look at the numbers. After this, once we are done with this one, if we are in quadrant number 1, in quadrant number 1, whatever theta is, we will take that theta. In quadrant number 2, we will do what? We will
Pi minus theta.
pi minus theta. In quadrant 3, we will do what? pi plus theta. In quadrant 4, we will do what? 2 pi minus theta. So we know theta is pi over 3. Now we will look, so we will not write theta. So what is the value of theta which give us these numbers 1 over 2 or square root 3 over 2? That is equal to pi over 3. So our theta is actually 2 pi minus pi over 3. So 6 pi. Okay, there is another way. You can write negative pi over 3. So 6 minus 1, 5 pi over 3, or theta equal to negative pi over 3. Either one you can write. Both are correct. Therefore, Z can be written. And you know this from your math 201 also, when you learn polar coordinates, that polar coordinates of a point are not unique. Yani one point in space in 2D plane, one point can have infinitely many different polar coordinates. Infinitely many. You can make r as positive or negative. You can make theta go as many circle as you want, adding 2 pi each time. So it is not a unique representation. So z is equal to r, which is 2, and then you can write cosine of negative pi over 3 plus I sine of negative pi over 3. In polar form. And when we take the value of cosine negative pi over 3 or sine negative pi over 3, we will go back into 1 minus 3 square root 3i. 1 minus square root 3i. Now, in complex numbers, the multiplication and division is like this. Multiplication and division of complex numbers in polar form. Multiplication and division of complex numbers in polar form. So let us assume that we have one complex number z1 equal to r1 and cosine of theta 1 plus I sine of theta 1, z2 another complex number r2 cosine of theta 2 plus I sine of theta 2. Then their product multiplication by simple multiplication rule z1 z2, but you will see what do we get at the end, is equal to r1 r2. Now what is inside the brackets, we multiply them, so we get cosine of theta 1 cosine of theta 2 real part and minus from I square sine of theta 1, sine of theta 2 plus imaginary part with I cosine of theta 1, sine of theta 2 imaginary plus sine of theta 1 and cosine of theta 2 is also imaginary. So we have this with big bracket close. So this is equal to R1, R2. And you know that from the trigonometric identities that cosine theta 1, cosine theta 2 minus sine theta 1, sine theta 2 is actually cosine of theta 1 plus theta 2. Similarly, cosine theta sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2 is equal to sine of theta 1 plus theta 2. So when we multiply complex numbers in polar form, then the product is equal to product of their moduli, yani product of the modulus, R1 and R2, they are modulus of these complex numbers. So product of R1, R2, then in the bracket, we will have sum of their angles. And when we divide, similarly, when we divide Z1 by Z2, this will be equal to R1 over R2. And then inside the bracket, it will be cosine of theta 1 minus theta 2. Cosine of the angle for upper number minus lower number plus I sine of theta 1 minus theta 2. And theta R is called modulus of, yani let me write it as a note. R is called modulus or absolute value of Z. And theta is called argument of Z, which is denoted by ARG, which is denoted by ARG of Z. And modulus of Z is denoted by Z modulus. So R is equal to Z modulus and theta is equal to argument of Z. Okay. Then there are few examples. Now I will do more after this from this section tomorrow, inshallah. Now it is time to end the lecture. Let me take the attendance and stop recording. And now if you